Alright, so that should have taken care of, in the previous video, the conversion of a regular expression um, that into a non-deterministic finite automata that recognizes the language that is described by the regular expression. And now we need to get to the second portion of our proof for the theorem that regular languages and regular expressions are equivalent in a sense, and that is the only if direction. That we cover it under lemma 1.60, which states that if a language is regular, then it is described by a regular expression. Now, the idea for this proof is that we will now need to show that if a language A is regular, then there will be a regular expression that describes it. We use our definition of regular languages, that if a language is regular, then it is accepted by a DFA. So if we have a regular language, we will create a DFA that recognizes it, and then we use a procedure to convert this DFA into an equivalent regular expression. Now, remember what happened with the time that we wanted to do the proof by construction on the closure properties, and that we used DFAs, and then we showed that for concatenation we can't really directly use the DFAs, although we could, but it would take a long time. And it was complicated, so we built a new toolbox. We're going to do the same thing here. We're going to build a new toolbox. So what we will do is that we will break the process of constructing the regular expression off of a DFA that recognizes a regular language. We'll break this procedure into two parts. And the way that we will proceed with this is with a new kind of finite automaton that we call generalized non-deterministic finite automaton, or GNFAs. And first we show that we can convert a DFA into a GNFA, and we build a procedure to do this conversion. And then we build a procedure to convert any number of any GNFA recursively into a regular expression. And when we're done with this, then our proof is complete. So let's first describe a GNFA, and let's see what a GNFA looks like and what it is. And then we will go ahead and work with the procedure and the steps. A GNFA is a non-deterministic finite automaton, or an NFA, in that in every step or in every state it may have multiple ways to proceed out of that state with the same strings or with the same expressions. So that's the non-determinism part of it. But we call it a generalized NFA in that at every step, instead of reading, or rather each transition from one state to another state, instead of that transition being taken place over one symbol of the alphabet, it will be taken place over a regular expression. So a generalized non-deterministic automaton basically will read blocks of symbols from the input, not necessarily just one symbol at a time, and then will process that block of symbol, and then they transition over the block. So the GNFA's moves along a transition arrow that connects two states happen over reading over a block of symbols from the input, which themselves are made of strings described by the regular expression on the arrow. So if you look at a GNFA, and I would try to write a certain transition, for example, for a GNFA, you may have some state that transitions into some other state. So if in a regular NFA, the label would be a symbol or would be epsilon. For a GNFA, this label will be a regular expression. And so this transition will happen when you are in state A and then you go to state B over reading the string that is described by this expression. So for example, if this expression is A, B, star A, then your transition will happen if you read from the string that's coming in something like A, B, B, A. So you read this whole block and then you transition from A to B. In a regular GNFA, in a regular NFA, you would basically read each symbol and then you would make your transition in that regard. Now, there's one special property that would require our GNFAs to have in order for this process of construction to be simplified. So what we are going to do for convenience is that we will require our GNFA to be in a format that has these three properties. The GNFA will have one start state, and this start state will have only outgoing transitions. So if I have a GNFA, there would be one and only one start state. Let's call this start. And then this start state will only have outgoing transitions out of it. So for example, something like a transition over the expression B or the expression AB star. And then we will also require this special GFA to also have only one accept state. So if we call this accept, then this state will be the machine will only have one accept state, and then it will have only incoming transitions. So the accept state will have only incoming transitions from other states into it, and then with all the other non-accept and non-start states, we would require the state to have exactly one outgoing transition per pairs of states. So for example, it would be AA, and then for example it would go from that state over the expression AB or BA into the accept state, and then we'll have, let's say, another state here, and then this goes with AA star, and then A, and then here let's say that this is B star, and then to itself with an AB, for example, and then to go from the accept state to the start state. So if you look at this generalized NFA that is in this special format that we require it to be, this generalized NFA will have a one start state, will have one and only one accept states, and every state that is not, and then the start state will have outgoing transitions to every other state. The accept state will have incoming transitions into it from every other state, and then any non-start state or non-accept states will have one outgoing transitions to every other state in the machine, and therefore they will also have one incoming transition into them. Notice that we also may have transitions labeled phi, and that means that this transition will never be taken. So transitions that are labeled phi are not taken. So if there weren't any transition between a pair of states, we would consider that there is a transition between them. In fact, in the case here, in the case up here between the start state and the state in the middle, there is a state transition labeled phi, but that represent that start state will not go to the intermediate state in the middle here. So this is the definition that we need. Now, the proofs that we will consider at this point to create and to basically represent our construction is effectively twofold. We first take our DFA and we convert that DFA into a GNFA in the form that we described, a GNFA that has only one start state, only one accept state, and then every and then start state will have outgoing transitions to every other state. The accept states will have incoming transitions from every other state, and then intermediate states will have one transitions going to every other state. So if we have a DFA, we can convert it into the GNFA in the special form. Then we simply, and to do that, we basically simply add one start state and one accept state. We make the start state to transition into the start states of our original language or original DFA, and then we'll make transitions, epsilon transitions, from all the accept states from the original DFA into the sole accept state. And then if any arrow have multiple labels on it, then we represent that with a union of the previous labels. And then if we have missing arrows, we basically put arrows with a phi label. Now from here on, we can assume that any DFA will be easily done and converted into GNFAs in special form. Now that we have that, we create a procedure called convert that takes any GNFA with k states and convert it into a GNFA with k-1 state. Except that when you have two states. If you have two states, and since this machine is a GNFA, the two states must be one start state and one accept state. At that point, we stop the process of conversion, and then the label that connects the accept state to the start state, or rather the start state to the accept state, then that label will be indeed your regular expression. And then we'll prove that this expression effectively performed the conversion accordingly. So let's draw this and outline it. Let's say that you have a 3-state DFA, and let's call it a 3DFA. So you've got a start state, a second state, and an accept state, and then there are transitions going back and forth, and so on and so forth, right? So if you start with that, then what we're going to do is that we are going to add a start state, an accept state, and all the transitions that are appropriate to make this into a 5-state GNFA. Then from this 5-state GNFA, we perform our convert procedure to convert it into a 4-state GNFA. Then we perform the convert procedure again, and this makes it into a 3-state GNFA. We perform the convert procedure one more time, and this makes it into a 2 GNFA. And when we have this 2 GNFA, then it would have a start state and it would have an accept state, and then one transition labeling them, and this transition would be your regular expression. Okay, so let's see how we first do our conversion of a 3DFA to a DFA to a GNFA, and then when we get to it, we'll take a look at the conversion procedure, and we'll see how it's going to happen. So then the idea then in how we convert DFA to NGFA and GNFA, generalized NFA, in the special form, and how the process works. So if you have a DFA, then your DFA basically has a Q set of states, which is going to be the set of your states, an F set of accept states, and a Q sub 0, which will be your start state. Okay, so we want to convert this into the GNFA. So what we are going, let's say that then we have something like Q sub 0 here and a bunch of intermediate steps or states, and then an accept state, or rather a set of accept states. So there's going to be a bunch of them. So how are we going to convert? So this is our DFA. So DFA looks like this, and let's see how we convert this into a GNFA. So this guy has an incoming state, right? So what I'm going to do is that I'm going to add and create a new state and then call it a start state. And then I make this state to be to transition into the Q sub 0, which is my the start of my machine. And then I'm going to add a start state here, and then I'm going to make all these guys to transition to it. And now I have only one accept state left. So an epsilon transition takes you from your newly generated start state into the old start state, and then all the other old accept states with epsilon transitions would transition into your newly formed start state. So then this will be a machine that will have the form of a GNFA. Okay. Now there may be a state that may be labeled, a transition that may be labeled with multiple states, or there may be multiple arrows kind of sort of going. All we need to do is then to remove these and replace them with one arrow, and then the label would be the union. And so we take care of all these, and when we have multiple arrows, then we basically replace them with a regular expression, so that uses union. And finally, if there aren't transitions between states, we basically add a transition and we'll label it phi. And since phi transitions are not taken in that there aren't any blocks of symbols that follow that transition, the language of this NFA will not be different than that of the DFA, the original DFA. And so from this point on, we can convert easily, make any DFA into the GNFA in the special form. So now that you have your GNFA in the special form, you can perform the conversion from the GNFA with K states, make the replacement, and convert it into a GNFA with K-1 states. Let's see how we're going to actually do that. Let's suppose that you have a machine with K equals, so actually let's see how this actually works. So if your GNFA has K greater than 2 states, then you would have a start state, an accept state, and at least one more state. Then what we're going to do is that we're going to look at a pair of 3 states. Then we take 3 states and basically rip one out and then repair all transitions in our machine. So then we process this process over and over again until our GNFA has K equal 2 states. When we have K equal 2 states, then it's going to look something like this. One state, the second state, and a transition between them. And so this state must be a start state. because our GNFA is in the special form, and so GNFAs have a start state, and therefore the start state also has only outgoing transitions, right? So it's not going to have a loop to itself. And then the second state must be an end state, or an accept state, rather. And since the accept states only have incoming transitions, then and no outgoing transitions, there's not going to be an outgoing transition out of it. So this is going to be your accept state. And then the label here is going to be your regular expression. And by the way, when we take the state out, this must be a non-start and non-accept. So we're not going to rip the start state or the accept state out, because that would alter our language in an irreparable way and fashion. So let's see how we can actually do this conversion, and see an informal procedure for the conversion before we actually go ahead and start looking at a formal description and a formal representation for it. So let's say that we have a machine, and so it's got a bunch of states, and then we are actually looking at 3 of its states. Q sub I, Q sub j, and Q rip. Okay. Now these are going to have transitions, right? So what I'm going to do here, I'm going to represent with the black arrows the transitions from Q sub I either directly to Q sub j or through Q rip. So let's say that the transition from Q sub I directly to Q sub j is R sub I, and Q sub I to Q rip is R1, and then Q rip to Qj is Rj. And then let's suppose that we have a actually I'm going to use green arrows or rather blue arrows, let's say, for transitioning self transitions. So let's say here we have R sub 2, and then for Q sub I, let's call it R sub 5, and for Q sub j transitioning to itself, R sub 6. Okay, and then I'm going to use the green arrows for the transitioning of Q sub j to Q sub I. So Q sub j to Q sub I, either directly or through Q rip. So these transitions, I'm going to call them with the red arrows. And so let's say Q sub j directly goes to Q sub I with R7. With R8, we are going to go to Q rip, R8, and then R9 is going to be from Q rip to Q sub j. So now the idea here then is to do something like this, to take this Q rip and take it apart effectively, rip it out of your machine. So we rip this off, and then we are going to repair all of the transitions in any pair that is left. So when we take the Q rip out of the machine, then I would have to go for every other state in the machine and repair its transitions from itself to any other state that's left, that go through Q rip. If there aren't any paths from 2 states, let's say K and L, through Q rip, there's no need for me to make any repairs on there. But if there is any changes, Q rip, I would basically need to make the repairs on the transitions. What that means is that I should also include self transitions. So here then, when I take this apart, then after transitions, so then after qrip is ripped out, then I'll be left with two states in this particular machine. So I'm going to have two states, so it's going to be a q sub I and a q sub j. And then there are actually four transitions that I'm going to have to take care of. The transition of q sub I to itself, the transition of q sub j to itself, the transition, which I'm going to write it with a black arrow, q sub I to q sub j, and the transition of q sub j to q sub I. And then to fix those, I'm going to perform the repair operation. So how does the repair operation work? Let's first take a look at q sub I to q sub j. Let's see when we go from q sub I to q sub j, what should happen. So what should the transition here, what does this transition look like? So let's call this r sub I j. Okay, so what should r sub I j look like? I need the r sub I j to effectively recognize the same expressions that my original machine would look like with qrip inside of it, which means that it is the transitions, the union of all transitions from q sub I to q sub j, either directly or through qrip. So it would be the transition q sub I to q sub j directly, unioned with q sub I to q sub j through qrip. Okay, so let's see how that looks like. So q sub I to q sub j directly is r sub 4. So this portion is r sub 4. And union with, now the portion that goes through qrip. Let's see how we can go from qi to qj through qrip. From qi to qj, we go to qrip, and then we may stay in qrip if there's a self arrow, and then we can go to qj. So it would be 3 concatenations here, right? Going from qi to qrip, concatenated with going from qrip to itself, and then going from qrip to qj. So there's 3 operations there. So the first operation here, going from qi to qrip, there's only one possibility. You take r sub 1, concatenated with. Going from qrip to qrip, you may take r sub 2, but since it's a self loop, it might happen over and over again, so it might be either 0 or more than 0 transitions of r sub 2. So it would be r sub 2 star. And then finally, going from qrip to qj, going from qrip to qj takes r sub 3. So it's concatenated with r sub 3. So therefore, this operation will be the union of r sub 4, union with r sub 1, r sub 2 star, r sub 3. And so this is the transition between q sub I to q sub j. So so then r sub ij will be effectively that. So this is going to be my r sub j, ij. Now how about how about this red transition, r sub ji, r sub ji, going from q sub j to q sub I. Same process, going from q sub j to q sub I will be the combination of either going from q sub j to q sub I directly union with going from Q sub j to Q sub I through Q rip. Okay, so going from Q sub j to Q sub I is going to be an R sub 7. So this is going to be equal to R sub 7, and then union with, then going from Q sub j to Q sub I, you could go through Q rip, so you go from Qj to Q rip, so it's going to be the concatenations of Qj to Q rip, concatenated with going from Q rip to itself, concatenated with going from Q rip to Qi. So, and of course, this portion is going to be R sub 8, concatenated with R sub 2 star, concatenated with R sub 9. And so therefore, the R sub ji is going to be R sub 7 union with R sub 8, R sub 2 star, R sub 9. So this will take care of my R sub ij there. So I'm done with R sub ij and R sub ji. Now there are two more transitions that are left. These blue self transitions from Q sub I to itself and Q sub j to itself. So how does this happen? So for R sub ii here, so for R sub ii, I'm basically looking at how Q sub I would transition to itself, and I want to make that take into account the state that I took out. So R sub ii is going to be either going from Q sub I to itself directly, union with going from Q sub I to itself through Q sub rep. Okay, let's see how that happens. So Q sub I to itself, this portion would be R sub 5. So you can directly go from Q sub I to itself through R sub 5, and then this will be unioned with, however, you can go from Q sub I back to itself, but this time going through Q rip. Now how does that happen? You might take R sub 1, so you go from Qi to Q rip, and then concatenate it with staying from Q rip to Q rip, and then taking from Q rip to Qi, just like we did with the previous one, right? So this portion is the black arrow, R sub 1. So this portion is R sub 1. The second portion is just like the previous examples, it's R sub 2 star. And then finally, the third portion is going to be the red transition Q rip to Q sub 9, so it's going to be an R sub 9. So then the R sub ii will be R sub 5 union with R sub 1, R sub 2 star, R sub 9. With the same token, R sub jj will be R sub 6 union with R sub 8, R sub 2 star, R sub 3. Okay, so then this will be the R sub jj. So will be that. And so with this format, then we have converted our 3-state machine here into a 2-state machine. So Q sub I will have a transition to itself, which will be R5 union with R9, R2 star, R1, sorry, backwards, and then Q sub j. I'm just rewriting these guys, so it's going to be R6 union with R8, R2 star, R3, and then transition from I and j will be R4 union with R1, R2 star, R3, and then going back from I to j will be R7 union with R8, R2 star, and R9. Okay, so this procedure, we call this procedure convert G. So if G was this original machine, this convert G will result in a G prime, which will be a machine with one less state than G. And this is how this conversion will take place. And but by doing this, we ensure that the new machine recognizes the same language that the original machine did, because when we take the state out, we make sure that each transition from every other state, including the states to themselves, will basically take into account the portion that went through QRIP. So later on, I'll talk a little bit more in a formal way about why this computation is true. But if you want to think about it, with this machine, we do a proof by induction. If the machine has only two states, then by nature we stop our operation, and therefore the language is recognized. If the machine has more than two states, in fact, if it's true that this procedure is true for k minus state, k minus 1 states, if we perform this on k states, if there are no paths through the state that we're ripping out, then the expressions for those transitions stay the same. If there are transitions through Q sub rip, this operation that we do here, this convert operation here, it basically ensures that the transitions are taken care of by including the missing transitions into the regular expression, and therefore the machine would recognize the same language. So from this point on, then the process will be fairly straightforward. We would have to formally define what generalized non-deterministic finite automaton are. When we define those, we define their computation more formally, and then from that point on, we will basically be able to perform the stepwise operation and give the algorithm, recursive algorithm for convert G, and that completes our proof. And finally, when we did that, then we'll see a couple of examples about how we can actually do this conversion of a finite automaton into a regular expression. So we'll do that in the next video.